Good morning, everyone. Hope you are all enjoying the session. So, myself, Dr. Chandranath Adak, currently Assistant Professor in Department of CSC here at IIT Patna. So, today we will see some basic mathematical background of logistic regression. Start with logistic regression, then we will talk about neural network, mathematical foundation, what is feed forward and what is back propagation, and internal details. And these lectures will be continuing. So let's see like how much I can finish. Okay. So my talk will be mostly based on neural network and convolutional neural network, upcoming maybe recurrent neural network and some advanced topics as well. Okay. And my details you can find over IITP website, my personal details, or what in which domain I am doing research, all the details. Okay. So I believe everyone having the knowledge of what is supervised learning, unsupervised learning, what we will call feature, what are labels. So yesterday's lecture, these parts has been covered. Okay. So today simply I will start with the logistic regression. Here, what is our objective? So objective is to classify a sample represented by a set of features. Okay. So I believe you know what is feature, what is sample, okay, and what classification does. What is classification? Supervised, right? Supervised. Okay. And we will talk mostly now. We'll start logistic regression. Okay. And in classification, what we do? Say our here in classification, our task is, or the aim is to find class label given a set of input features. Input features that say input feature I am denoting as a k dimensional real number, say r to the power k. So dimension of the feature is or k dimensional feature vector. So one sample we denote using a set of features or k dimensional feature vector. Okay, clear? So how the sample will be here? Say if we say say I have x and this y. So here x is my this input feature that is of k dimensional, maybe one number maybe, or maybe it's a class labels. Say if I say example binary classification. So I'm giving some examples. Say maybe say two animal image, maybe one image is of cat, another image may be dog. So we'll calculate some feature from these images and our class labels will be maybe cat dog, but suppose I am denoting using 0 and 1. So y will be either 0 or 1 and take, suppose I have extracted say k dimensional feature vector. So this. Clear? Any doubt up to this? Okay. So now what we will do, we will or any some let's go back. So some another examples of classifications maybe in this I have given the example of say computer vision domain where the input is your image. Okay, say input if your image. So I am giving one example of cat versus dog image, means like two classes. So maybe say in the text domain when your input is text, maybe there's some Twitter comment, say whether these are say hate speech or non-hate speech in this one. Okay, so input is your text or maybe say now not Twitter, say X. This is that brand. Okay, and hate versus non-hate, or maybe in email you have seen that spam versus non-spam in this way. But there maybe the uh, input may be multimodal. In email maybe you have images as well as text. Okay, so combining that like image plus text input and output maybe your spam or non-spam in that context. Okay, email. Okay, and so one thing you can observe, I believe. So whatever the input we have to convert it here for further processing into some numerical value. So whether maybe it is image or text or anything. Okay, it is better to convert in terms of numerical values. Okay? Because you all know that the computer understands only binary numbers 0 and 1. If we convert some decimal and maybe after that we can convert into some binary. Clear? Can you give some example of where the input is directly some number? So here I have given the example of image and text. So my next question is say input is some sort of numbers and you would like to classify into something, some class you have, maybe class 0 or class 1. So maybe you can think of some, say weather, maybe class, maybe whether is rainy or say non-rainy or not rainy. So yeah, so weather related data like humidity, maybe some other, maybe temperature in this one. Getting my point? So those may be numbers, say humidity, temperature in this way. So each value will be your one feature value, right? So altogether a particular region, particular for a sample point. So here maybe I have say 5 samples. So what will be the value of k? 5. Okay. So let's go to. So let's see some basic examples. Suppose you have plotted some point, say here maybe this one, and here maybe say maybe this one, another class. Okay, so this is zero class or circle class, cross class. Okay, say based on some feature. So how you will draw some decision boundary so that these two classes you can separate. So let's give me some example. If you draw this line, so left hand side will be cross class, right hand side will be the circle class, right? You can differentiate two class, it is easy. Getting my point? So maybe this is one. Okay, but but which line you will select? Say this one, or maybe this one, or maybe this one. So which one? That is challenging, right? Or maybe if your data looks like then it will be hard to draw some boundary, right? So if I draw in this way, so some points maybe if I draw this line, some point may be here, some point may be here, right? So this, then how to deal with it? So at least you have understood that only simple line will not suffice our purpose, right? Getting my point? So only a simple line. So that's why we may need some non-linearity. So here what we will do, say one thing, if I draw some sort of, say, maybe line. So if this point, okay, this point may be my, if I consider this is 1, so this will be my, say, threshold. Okay, I will come into detail of this. So the span of this line h theta, if I call, or the span of h theta is from, say, minus infinity to positive infinity. Okay. So that means this line's value, so if I consider this is 0.51, so this h theta value may be more than 1 and also less than 0, right? Okay. So what I will do and which line I will choose, so that is some bigger question. So for that reason, we need to know some existing functionality, that is we will learn now sigmoid. So this sigmoid function, sorry, so it will look like, so if it is 0 and if this is 1, so this, and if this is, say, 0.5, so this line will look like this. So some sort of, say, S line. Okay. So pardon my drawing. So this way it will look like. What will be the formula? Say if this is your, say, maybe if I consider this Z, the sigma Z, this y axis is your sigma Z, the sigmoid function. I am denoting sigma Z. So it will be 1 by 1 plus e to the power minus Z. Okay. If you plot this thing, you will get this red color curve. So this is giving us some non-linearity. So some interesting fact is here, say that characteristics of sigmoid function. Of sigmoid function, that is it is 0 less than equal to sigma Z less than equal to 1. So sigma Z, let me write it down, 1 plus e to the power minus Z, this is less than equal to 1, and sigma 0, this value is what I have written in the curve. Can you check and tell me? Equal to, no, instead of Z you just put 0, 1 by 1 plus e to the power 0, 1 by 2. Okay. And here input of this sigmoid, what will be? Input of sigmoid here is Z. Okay, the sigma Z. how this z we are calculating? So last day Dr. Sudhir mentioned, right? Theta I xi or wi xi, remember? So at first we have some linear combination. So when I will cover the neural network also, it will come more detailed. The objective of telling the logistic regression is to mention about the cost function, how we deal with the cost function. So this z equal to sum over I, say theta I xi. So if I consider say I equal to 0 to say what will be the limit? K, right? I am considering k dimensional feature vector. So this is what? Theta 0 x0 plus theta 1 x1 plus dot 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 plus theta k xk. So here what we do, this one we consider this x0 we consider as 1. So that means x0 equal to 1 if I consider, then theta 0 plus theta 1 x1 plus theta k xk, right? So theta 0 like I am taking as bias. So theta 0 is special term. So why this bias is important, I will come into that also. Okay? So now one interesting fact, if I tell you that when this remember this one is very important. So theta z equal to 0.5, this can be used as threshold value. What does it mean? So whatever sample you have, say sample x means like I have denoted one sample in terms of k dimensional feature vector. So k is nothing but this x1, x2, xk. This will belong to some positive class. Positive class means that upper part maybe is that circle class, and negative class maybe that cross class. So here yeah, this one I am denoting say maybe negative class, this one as positive class. Okay, in this way. And when is it positive class, can anyone tell? If so, I am considering this as threshold. So that means if sigma z greater than equal to 0.5 and it is in negative class, if sigma z or simply write otherwise. Someone is saying sigma x. Someone is saying. So just mention. Look here. Okay. So input of sigmoid is z. So at first we give some linear combination. So input of sigmoid is some linear combination of what? So what is theta actually? All theta is. These theta i's are very important. So these theta i's are your some calls OHs, and sometimes in neural network we will denote this theta i's using wi's. Okay, in some book also the theta I or wi is almost same. Or we call this learning parameters. Learning parameters. So these are important. In machine learning, these learning parameters actually you are learning. Some learning, machine learning, we are learning something. These learning parameters we are learning. Okay, so what does it implies? This thing, sigma z greater than equal to 0.5 means this x is in positive class if Z greater than equal to 0, negative class, otherwise, because these and these are synonymous, right? Clear? So now let's do some task. Say say I have this z equal to theta 0 plus theta 1 x1. Okay, this has been given. The task is we need to predict what we need to predict or what we need to learn. Predict or say learn theta 0 and theta 1, right? Say here the task is to find class boundary. So it will be more clear if I draw one diagram. Just a minute. Let me draw one diagram. It will be good. So suppose I have here say these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this way I have these are the value of 0, this is 1. So we can consider this example in terms of binary class. This we call binary classification. Say in medical domain, maybe say for tumor, say benign or malignant tumor classification. So in this way you may think of. So here I have samples, say this 1, 2, 3, 4, 5, 6, and here also I have some samples maybe in this one. Okay. So here you can think of some decision boundary maybe at 7. Okay. But if you can plot, you can think of this one. But from this formula, this one, how we will define? So how we will calculate? So for example, here assume say theta 0 equal to -7 and theta 1 equal to 1. Then what will be your z? Calculate. Z will be -7 plus x1, right? So what you know from the positive class, that sigma z greater than equal to 0.5, we are considering positive class, right? So what does it imply? That z greater than 0. So what does it mean? -7 plus x1 greater than equal to 0. So that means what? X1 greater than equal to 7. So what is your class boundary? So your class boundary will be what? X1 equal to 7. So it was suppose x1 was your 7. That was your class boundary, right? So this is easy. Some say some another data plot. If we consider say I have some classes I have plotted. So I got this is one class. Another one I am getting as say so now it is hard to. So I have two classes here. By visually you can see one is cross, another is circle, right? So you can't draw some line here, right? This thing you have understood, right? We can't draw one line, but still we need some decision boundary. So by using your common sense, what will be your decision boundary? some circle one, right? So this may be your decision boundary. Pardon my drawing. So this is considered one circle. So obviously, if there is a circle, there will be a radius, right? So remember this thing. So suppose for this one, for this case we are considering, say I have, suppose I have this z equal to this theta 0 plus say theta 1 say x1 square plus say theta 2 x2 square plus theta 3 say x1 x2 plus theta 4 say x1 plus maybe theta 5 say x2. Okay. So is this a linear combination? No, right? Okay. So now if I consider, so what you need to do here? So you need to learn this all thetas you have to learn, right? Or at least predict all theta is theta 0 to theta 5, theta 0 to theta 5. Yeah. So say sorry. So you assume say theta 0 equal to minus r square. What is r? That radius. Just to consider. Consider this theta 1 equal to 1, theta 2 equal to 1, and all others say theta 3 equal to theta 4 equal to theta 5 equal to say 0. Now what will be your z? Please calculate. Everyone please do use your pen paper. So z equal to, so theta 0 equal to minus r square. So minus r square, then plus x1 square plus x2 square. So what we know for the positive class, we will use the same rule. Say theta z greater than equal to 0.5 positive class. Okay. So theta z greater than equal to 0.5. What does it mean? Z greater than equal to 0. That means minus r square plus x1 square plus x2 square greater than equal to 0, right? So in other term, x1 square plus x2 square greater than equal to r square. So what will be your decision boundary? Decision boundary x1 square plus x2 square equal to r square. Now you are getting this circle. Okay, so this thing may be your r. Okay, clear?
But like we want to learn the theta values, right?
Yeah.
But why then? What's the point?
So here just I am giving some example. We have not learned yet.
You're saying that this is the theta values that.
Yeah, that I am giving you
Yeah, like.
for knowing the decision boundary.
But by learning that if we get something like this, it is good.
So that how to learn that will come now. So for that we need to know some cost function. So in regression, it's just terminology. So here in regression we call something. So we call something. This is hypothesis. This term you heard of in linear regression. So we denote this using h theta I, or maybe sometimes we also write this h theta of xi. So it is not that x to the power I. So this thing is equal to 1 by 1 plus e to the power minus of what I will write here. So remember the sigmoid formula. What was that? 1 by 1 plus e to the power minus z. So what was our z? Sum over I equal to 0 to k theta xi. Remember? So that we will put here. So here I have denoted using I. So that's why I am denoting that one using 0. So j equal to 0 to k theta j xj, that you know. Now this I means just ith sample. So let me quickly draw one thing. So suppose you have these points, okay? So how many points I have? 1, 2, 3, 4, 5, 6, 7, 8. So here I have I equal to 1 to 8. Clear? So each sample, suppose denoted by say maybe say 20 feature dimensions. So here I have 20 values. Okay. So here each sample is denoted by say r to the power this 20. That k, remember k equal to here 20. So k equal to was our 20. So j, this one is varying from say this one. Okay. Clear? Okay, so here we are taking some convention from linear regression. So say as per linear regression, although I have not taught, I believe last day it was taught very clearly. So as per the linear regression, the cost, suppose I am denoting using this j theta equal to say I am denoting using this h theta I minus yi this square. So h theta I, you know, this one is what? Predicted value. Predicted. This one is actual. And we are squaring it up. So it means like squared error. But there are I number of samples. Here in this example, just to saw 8 samples. So all errors we have to average it out, right? So we are calculating all the errors for all the samples, then averaging it out. So what I will do? Average formula, that's sum divided by the number of sample. So that means you are taking sum I equal to say 1 to n. So n is your, so k was your number of feature for each sample and n is the number of sample. So you are averaging it out over this. Clear? So any special name it has? Mean squared error. So for sake of the mathematical computation, you know that the differentiation of the square term it will be 2 of that, right? So to cancel it out, we sometimes write this 2, 1 by 2n. So later on, like in neural network when I will teach, so there we will differentiate. So there it will be useful. So we talk this entire logistic regression for this only cost function. Now the thing is, so one thing you just try to think in with some human intelligence. So actually something is there, you are predicting something. So what is your objective? Actual should be equal to the predicted one. Everyone is clear? So that means what? When actual is equal to predicted, it will be, the cost will be 0. Clear everyone? So our objective is to make this cost 0, or at least here the minimization. Okay. So if I think of say suppose this function is looking like this. So our goal is to reach over here, right? Minimization. So if I draw this one, say maybe say this theta, it will be your say j theta. So our objective is to reach over here. But this square function has some like some special property. Our objective is to make this curve like perfect, this U shape. But actually for this square curve, we will get the function like in usual case it will look like this. So what is the difference? This and this? Yeah, good. So it has multiple local minimas. That is the that will get some problem. So here, okay, we're doing many things, but the problem we face, j theta is no longer a convex function. Why not convex function? Because if I take 2 points, if I draw one line, so this line will be outside of that curve, right? In layman term, you can think of this. So it is not a convex function, but we need a convex function. So we have to convert this in some way. So why it is not convex function? Because it contain multiple local minimas. Okay. So what we need a cost function with a single minima. Okay. So I will copy this thing in the next slide. Remember this thing. I believe you have noted it down. So j theta equal to 1 by 2n sum over this I equal to 1 to n. It is not to the power I. Okay, this I believe you have understood. You can write in this way, or sometimes you can write in this way. Okay. Yji square. So this is 1 by n sum over I equal to 1 to n. This thing, now I am denoting this thing in terms of a loss function of h theta I and this yi. Okay. So this is a function of actual and predicted value. Okay. So now we will entirely look into this loss function. So if I write, okay, already it is given. If I write loss of this h theta I comma yi equal to minus of log of h theta I minus for if yi equal to 1 minus of log of 1 minus h theta I if yi equal to 0. Okay, this will consider. Why we are taking this? Why we are taking this? So what was our problem here? We have multiple local minimas. So converting into in some log curve so that we will have one single minimum. So for this we have to know how the log curves look like. So I believe you all know how the log curves look like. So so um, so this one, suppose this is 1. So this is your ln x, right? So if I consider this x,
How are they equal?
which one?
The left hand side and right hand side.
This
How are
and
they
this.
equal? Yeah.
So I'm just denoting this one as loss of this. Just denoting. Just this part I am denoting using this. Just writing as a function of h theta I and yi. That's it.
Yeah, but then you are defining that loss in terms of log, right?
Yeah, now I am defining this one. We can't use this one. Instead of this, I am defining this. Just denoting. Okay. Just that's not right. No. So j theta is what the meaning? J theta equal to some function of actual and predicted. Okay. For if I take all the sample, then I will take the average. Okay. So we can't use this loss function due to having multiple local minima. I am defining some new loss function. That's it. Okay. So this maybe you just write this colon equal to this. I am denoting. So this is the function of ln x, and what will be the this is minus of ln x. It looks like this. Okay. And another function. This is 0 and this one is 1. Okay. And suppose this is 1. So this, now I am drawing the function, this one. This function is minus of this ln of 1 minus x. So now focus on this one and this one. If I merge this thing, look carefully. So this is my 1. So this line is my what? Minus of ln of 1 minus x. And if I draw say this line, this one is for minus ln x, right? So now if you look into this one was our objective, right? So now you got the reason why I am taking this one, the loss function, in this way. Now if I combine this some concrete form, so it will be so combining both the cases, it will look like loss of h theta I yi, it will look like yi minus of log of sorry h theta I this plus 1 minus yi into minus of log of 1 minus h theta I. So look carefully this term. So see, when this one is 1, so this term will be there just like this, and this will be vanish out, right? Getting my point? Now if this one is 0, so this term will vanish, this term will be there. It's like this will come. Okay. So in this way we are combining. So there are some special name of this type of cost function that this will use in the later part of neural network. Okay. So now if yi equal to 1, so this term will be there, 1 into this term, so this will come, and 1 minus 1, so that means 0, this part will vanish, right? So only this part will come. Now yi, suppose I am taking as 0, so 0 into this entire term will vanish, and 1 minus 0, this term will be there, 1 into this, so this term will be there just like this. Okay. Up to this, any doubt with anyone? Okay. So once again and try to think. Now we will start the neural network part. That was our main objective. Okay. So so why the name is neural network? Like why some part is like neuron? Those you please read by yourself. Like some people say, okay, this imitates how human brain works, but to some extent like basic component. But the human brain are like very complex thing. But okay, in this domain some nomenclatures are there. Say maybe neural network is consists of some artificial neurons. Okay, what neurons, like, okay, that we will also talk. Like if it tries to model, like some people say tries to model like human brains or artificial neurons in this way. Okay, like, and this in human brain, just like it transmits signals to one neuron to another neuron, here also some transmission is there. So, but the main thing is it is. So here we will look into the mathematical foundation. For our case, this will be nothing but is a function that maps input parameters to outputs. So what these input parameters will call just now we talked about features. Okay. So that means neural network is nothing but we will look into in terms of some function. So what are the applications? Just one talk was there, right? AI. So all are the applications you may think of. Okay. So here we will have, look carefully this diagram. I will draw this multiple times, x1, x2, and this will be your z. So there will be connection in between. Suppose these neurons. So here what I denoted earlier thetas in logistic regression, now I will denote using W. Okay, they are the same meaning. So what will be W's here? W will be weights or learning parameters. Learning parameters that we will learn. And what are your X? So here X is r to the power 2. So it is x1, x2. Two features you have. So these xi's are your features, w's are your OHs. Okay. Now, so z will be what here? Okay, that I will come. So after that, suppose now you know what is sigmoid, the utility of that one I will also come, and you are predicting something. Y hat your so y hat is your predicted output, and in your training sample, so what's your objective? Let me write it down. X2 right here. Thank you. So your objective will be, what's your objective? To learn a function that maps the inputs to the outputs given some training samples. Okay, you should have some training samples, right? Last day we talked about this, like training and testing, training sample, testing sample, what are the validation sets, those. Okay. So how the training samples will look like here? Consider we are looking in terms of supervised learning. So obviously in supervised learning, what we'll have? In training sample, what we will have? This x1, x2 will have, and some y. So this will be your input feature, and this will be your label. Clear? And you would like to predict predicted output is your y hat. Okay. So that means how we will calculate the loss or cost? It will be some function of this y and y hat. Clear? And your learning parameters will be here W1, W2, and I will discuss on this a little bit later in detail, W1, W2 and B. So here I will have one bias component. Okay. So what does it mean? This your Z will look like W1 X1 plus W2 X2 plus B. This B is synonymous to that we talked about W0. So if you take W0 X0, X0 equal to 1, the same way you can write. So I will draw this diagram again. So take this note of this one. I will go to the next slide. Okay. So X1, X2, W1, W2, this bias component 1, this sigmoid, this y hat. Okay. So in the so we'll have two type of propagation. One is feed forward. In feed forward, how we'll go? We'll go in this way. Okay. So at first, what we will do? We will perform some linear operation. In linear operation, what we will do? Here z equal to w1 x1 plus w2 x2 plus b. So from this logistic regression example, we saw that linearity is not always sufficient. So we have to introduce some non-linearity. If your data are in can't be separable with some linear decision boundary. So that's why. So here you should make note. Linearity is not always sufficient. So that's why we have to introduce non-linearity. Non-linearity is introduced here in neural network in terms of, there is a special name, activation function. Okay, don't worry about the naming convention, it's just a name. So here for the sake of simplicity, at first we will use sigmoid activation function. That formula you know, just we saw. So it is easier to learn the logistic regression before this. E to the power minus z. Okay. Now what's happening? The output here I have drawn only a simple neural network, very basic. So there are some other terms like perceptron or single layer perceptron. We have multiple layer, then we will call multi-layer perceptron. So when we will have deep, very large architecture, multiple layers, we will call say deep neural network. So these are few names. The output is predicted through a, so in generic I am writing series, but here I have not denoted, series of linear and non-linear operations. Non-linear operations. Operations or say functions. So then finally what you will do? Finally you will calculate, after this series of operation, finally you will calculate loss. Loss is calculated as a function of what? Actual and predicted output. So say I am taking one example, say half squared error loss, or half squared loss. So this is, so suppose I am denoting using L of y hat, it will be 1 by 2 y minus y hat this square. So there is a difference between cost and loss function. So sorry, this cost is calculated over all the samples. So means like average over all the samples loss. Okay. So here I am calculating only, say, for only one sample's loss. So earlier remember we took the average of all the loss. So just in this slide. So average over all the loss. So this we are calling this cost. So because the calculation is a little tedious, so here I will consider in this example only the loss. For only one sample I will show you, you can do it in your way, or better in computer science what we do, we introduce the concept of vectorization at one go using some concept of some matrix. All the samples are there, we are perform. So that's why Python in these days like so much powerful due to the vectorization. Okay, this is the feed forward. In this way we have processed. Okay, now what will be your, now the thing is we have calculated the loss, okay, but then you have to give some feedback. Why we have to give some feedback? There is reason. It is not randomly we are forwarding and then okay backward, or there is special name that is back propagation. This is your feed forward, this will be your back propagation. Why we need to propagate back? So can anyone tell? To? Yeah. So in yeah, is right. So our objective was to minimize the loss. In the ideal case, the loss will be 0, but it may not be possible. But at least to minimize the loss. So in the first go, we have started with some value of W's, or the learning parameters. If someone asks that thetas, I just took randomly, right? But in some logistic regression example, so how I got to know that one, that we are actually learning. So initially we arbitrarily took some Wi's, but it is suppose giving me like higher amount of loss. So that's why I have to propagate back and change my W's, or there will be some formula that we will call to update this OX. For update OX, we will have some optimization function. So far we have looked into 3 types of function. So one is this activation function. What is the purpose of this activation function? To achieve the non-linearity. We have learned some loss function. We have learned to calculate the loss, or to measure some difference in between, say, actual and predicted one. And this optimization function, it is very, very important that we are actually optimizing these WIs. Optimization function to update OS or to optimize the OS. So these 3 things you please remember. If time permits, I will take some dedicated classes on this activation loss and this optimization function. Okay. So now the back propagation. In the back propagation, is very, very simple. That is the error is propagated back to adjust the that's wi's or these learning parameters. Okay. And in back propagation, what is our objective? So be very clear about these points. What is our objective? Objectives to update wi's to minimize loss. Okay. Okay. For this example, we'll look into in terms of minimization, and some example. We'll also talk popular optimization technique. One of the popular optimization techniques are gradient descent. Okay. Now what we will do in today's class, the example we will take. Say I am taking an example of illustration. So an example for illustration. What we will do? We'll learn the Boolean OR functionality. So Boolean OR, I believe everyone knows this. This one is your what is y label, right? So 0. So it is a Boolean OR. So 0 0. What will be the actual output? So we are taking x1 x2 as feature, and this is our actual label. So 0 0 0, then 0 1 1. All other cases it will be 1, right? So I will show you in only for this example. Okay. So only this sample I will take, and our objective will be to label it as 0. This example I will show, but in computer we will perform at one go in terms of vectorization. But here we will see how we will calculate the mathematical background. So here if I plot, this one is x1, this one x2, how it will look like. Say this is 0, this is 1. So this is also 1. So 0 0 point is what? 0, right? And 0 1 point, so this point is 0 1, right? So this I am giving cross. So 1 1 point is 1. This 1 1 point is 1. So here I am giving cross, here I am giving circle. Okay. So this we are trying to do. So our objective here to train a neural network so that it can learn Boolean OR functionality. Clear? Clear about what is your feature, what is label, and we will predict y hat. So this diagram I have to draw multiple times. So this W1, W2, and here we have this bias component. So what was our example? So input for first sample. So one sample I will do. Input for first sample, x1 equal to 0, x2 equal to 0, right? So I am initializing the weight, initialize weight randomly. So I will optimize this weight, but at first I am taking the weights randomly. So W1 equal to say 0.2, and W2 equal to say 0.5, and B equal to 0. Now you calculate the feed forward thing. So we have to do. What you will do? Calculate what? Z. Good. So Z will be W1 x1 plus W2 x2 plus B. What will be the value?
0.2 x1.
So 0.2 into 0 plus 0.5 into 0 plus B is our 0, altogether 0. So y hat equal to sigma of this Z, 1 by 1 plus e to the power minus Z equal to 1 by 1 plus e to the power 0, right? So what will be the value? 0.5. So what will be our loss? So I am calculating for only one sample, that's why I am taking L, not J. This will be what I have taken, half of this y minus y hat square. Half of what is my y?
0.
Why 0? Anyone?
0.
Because actual level was 0, remember? So that's why I am giving 0 minus y hat. I have just calculated 0.5 square. You please calculate this value. Okay. Now this is feed forward 1, number 1 stage. Now what we will do? We will back propagate. So this one I am writing this L of y hat with respect to, I have taken W1 equal to 0.2, W2 I have taken 0.5 and B I have taken 0. In terms of this I have got 0.125. Okay, just in terms of whatever I have taken x1, sorry, W1, W2 and B, because that is our main objective. So I will update these W's. The next slide will be very important. I need everyone's full attention. W1, W2, this B. Okay. So this now I have calculated, suppose this loss. So here I will calculate del L by del W1. Why? I would like to know the rate of change of loss with respect to one parameter. That first I will check with respect to W1, then I will check with respect to W2, then we will check terms of maybe W3 in this way, maybe or also in terms of bias as well. Rate of change of loss with respect to this W1. So using some chain rule formula, like maybe class 11 mathematics or 12 mathematics. So if you cancel it out, so this will cancel out, like chain rule. Okay, clear everyone? So now we will slowly calculate these three things. Okay, so at first how to calculate this del L by del y hat. Everyone please calculate. What is your del? Sorry, what is your L? Half of y minus y hat. Sorry, square. So now 2 will cancel out. That's why I have taken 1 by 2, half square error loss. So 2 will cancel out. This y minus y hat, I am differentiating with terms of y hat, so that's why 1 minus will come. So if you put this value, so what was our y? 0. What was our y hat? Y hat we just calculated. Y hat 0.5. So 0.5. This one altogether 0.5. Clear? Any doubt? Now the second term, that is del y hat by del z. So what is this? 1 by 1 plus e to the power minus z. So can anyone please calculate quickly? So the lower part will be 1 plus e to the power minus z. So it's some basic thing. So you can do this. An upper term minus of e to the power z and minus plus. So how? Let me calculate. So minus of e to the power minus z and another for minus z. So e to the power z. This will come, right? Clear? So if you put these values, so you'll get easily. But there are some special type of like form. So how it will come? So if I put this one, so can I get this one 1 by 1 plus e to the power minus z, then minus of 1 by 1 plus e to the power minus z square. Can you please quickly check? So
here you're using gradient descent to backpropagate.
I have not come yet. I will come. Now only I am checking rate of change of loss with respect to one parameter. That's it. So those details I will come a few minutes later.
Using backpropagation.
Backpropagation.
Using which function?
In backpropagation, what we are doing? Update the WIs to minimize loss. So how I will update, that will come few minutes later. So are you getting this form? This is like basic algebra. Clear? So can I write this one, or I should explain this one? Okay. So if I take this one, 1 minus 1 by 1 plus e to the power minus z. So this is giving me a good form, that is sigma z into 1 minus sigma z. How it is coming? Clear, everyone? So now put this value. So sigma z was what? Sigma z was 0.5. So 0.5 into 1 minus 0.5 equal to, clear? Now what we will calculate? Del z by del w1 equal to w1 x1 plus w2 x2 plus v. What we will get? Is partial derivative. So we will only get x1 because x2 here and b are constant in terms of w1. So here we will get x1. What is our x1? From where we are getting? Have taken x1 is 0, right? Now if I put these values, say 0.5 into 0.25 into 0, so altogether it is coming 0. So actually our objective is to check del L by del W1. So slowly what we did, at first we calculate this one del L by, sorry, this one del L by del Y hat, then del Y hat by del Z, then Z, then sorry, this one then this one, then this path we have calculated, right? So another path we have to calculate now. What? This path, and this path. So again I have to calculate the del L by del W2. It will be del L by del Y hat into del Y hat by del Z into del Z by del W2. So what will be your del L by del Y hat? Same value, right? 0.5 into again same value 0.25. Now del Z by del W2 I have to calculate. Del Z by del W2 equal to del by del W2 W1 x1 plus W2 plus B equal to x2 0. So here also I am getting 0. So W1 previously it was W1 was what? 0.2, 0.5. Okay. So I will come to the weight update formula a little later, but you can see like here also 0. This one is also 0, and this one is also 0. Okay. So our savior will be this bias. So now calculate this one. Del L by del B, what it will be? Anyone? So that means the path will be now what? This one, and this one. For suppose you are taking say hundreds of learning parameters, so for individually we have to calculate del L by that del Wi. So del L by del Y hat by this del Z into del Z by del B. So first two term we have already calculated 0.5, 0.25. 0.5, 0.25 into that del Z by del B I have to calculate. Del by del B W1 x1 plus W2 x2 plus B. What will be the output? 1. So now 0.5 into 0.25 0.125. Clear everyone? Any doubt? Now we have to learn so see here what I told earlier, we have checked the activation function at sigmoid, loss function we have used this one, and optimization function we will see. So here I mentioned one popular optimization technique is gradient descent. So for that we will quickly look into, not in very much detail. Later on we will check in detail, but for now, for this calculation, the gradient descent, the formula is or say the code say you have to perform just a minute. In the gradient descent, GD I am writing in this way, gradient descent, here you have to repeat until terminated means like you have to put some termination criteria. What will be those we may discuss later, but the formula is Wi equal to Wi minus alpha into del L by del Wi. So left hand side, so in computer science you know, right? A equal to A means, so left hand side is the new A, right hand side is the old one. So left hand Wi is the new one, right hand side Wi is the old one. So here this alpha is your, just a minute. Learning rate, I am writing say ALR, learning rate. So details running out of time, maybe details we will discuss later. So learning rate we have. So how with the name, what does it mean by the name learning rate? means the rate of learning, or maybe the how fast you are learning. That if time permits, I'll discuss in detail. But for this time being, suppose only sake of the mathematical calculation, I am taking this, or in terms of mathematical easiness, like mathematical calculation easiness, I am considering alpha equal to 1. That should not be, but for sake of calculation. Okay. So this is in some sort of a loop. Now one epoch of GD is like one not one iteration, so one epoch of GD. What you have calculated? W1 equal to W1 minus alpha into, so this is Wi means like all the learning parameters. So del L by del W1, you have to calculate this. For the new W2, what it will be? W2 minus alpha into del L by del W2. Can you please quickly calculate for me? So earlier W1 was what? Yeah, earlier W1 was my 0.2, W2 was 0.5. 0.2, here it was 0.5. So alpha I have taken 1 for the sake of simple calculation. Del L by del W1 was what? 0, and del L by del W2 was 0. So there is no change in W1 and W2. So that's why I told that our savior will be that bias. So from this you can understand the requirement of this bias, right? Sometime, not always, sometime. Bias will be B minus alpha into, sorry, del L by del B equal to, previously bias was 0 minus 1 into, just we have calculated here, del L by del B means what? 0.125. So now we have completed up to this we have completed back propagation 1. So that means we have performed feed forward 1, then back propagation 1. Now second stage will come, feed forward 2, right? So in feed forward 2, or say FF2, what we will do again quickly? Z equal to W1 x1 plus W2 x2 plus B. So what is my W1 and W2? No change, right? So W1 was 0.2 into x1. X1 was what? X1 and x2 values you are getting from here. This one. 0 plus W2 value was 0.5, no change. 0.5 into 0 plus this B, previously it was 0, now it has been updated to minus 0.125, right? So altogether it is minus 0.125. Now y hat, you please calculate sigma of z equal to 1 by 1 plus e to the power minus z equal to 1 by 1 plus e to the power minus of minus 1.25, 0.125. It will be, you can use your calculator, I know the value. So Okay, if you use your calculator, you will get it will be approx 0.469. So now what you will do? You will calculate the loss, right? Loss of y hat equal to half of what was our y? 0 minus 0.469. Sorry, this one square. This you please calculate. Point 10.10 So this loss is with respect to W1 equal to 0.2, W2 equal to 0.5, B equal to minus 0.125. Okay, so suppose I am denoting using as say so I am denoting using as L2. So L2 I am getting 0.109, and earlier suppose I am denoting using say L1. L1 was 0.125. 0.125. So is there any observation from your end? So what was our objective? To minimize the loss. So after this, you can see this loss is decreasing, right? Okay, clear. So for only one example, we have seen this. So this is the thing. So now, okay, quickly we can see. So I have taken this alpha equal to 1. So there are a few comments. So alpha is your hyperparameter that you are not learning. You are giving explicitly to the system. But this wi is the learning parameters that you are learning actually. Understood the difference between learning parameter and hyperparameter? Hyperparameter from our own experience or empirically experimental setup we have to tune. For that purpose we are giving the hyperparameters, but learning parameter that the system is learning by itself. So I will discuss something, this learning rate alpha. See, so this was our curve, say this was W. So I have taken only one example, that's why I am writing LW, otherwise I would written JW cost. So tell me, if the alpha is very small, what will be the case? What will happen? So our objective is to go over here, the minimum. So alpha learning rate is very slow, so very small. So suppose it has start, so it is very small, it will take time to reach over here, right? So that means learning will be slow, right? But suppose alpha is like big value, alpha is a say big value, what will happen? So in layman time it will be fast, right? So here slow, it is fast. So is there any problem, like it is fast, so quickly? So but actually what will happen, it may jump at first here, at first here, at first here, here, maybe here. Okay, so that means it may, so jumping, like in terminology we say it is may, not always, sometimes it may overshoot the minimum value. and our ultimate aim is to come over here. So that means it may fail to converge even it may diverge. Okay, that is the problem. So empirically, experimentally, we have to set up this hyperparameter, not too small, not too high. Okay. So in general, like people start with say 0.1, some based on some data set 0.01 in this way, okay. Or 0.01 in this way. Some basic setup. But not obviously that one we have taken in the example. That was for this ease of calculation only. Okay? It is not always the case. Okay, so gradient descent we have learned. So whenever we learn some new algorithm, why we explore some new thing, because there is some drawbacks of the previous one. That is the common strategy. Obviously, there is some problem in gradient descent. So problem of gradient descent, one of the problem is it may stuck in local minima. So local minima is what? Suppose you have this curve. Okay, I have not drawn correctly. So this your global. Suppose this one is your global minima. This one are your local. Okay? So this one W, this one say LW or say JW also you can think of. So gradient descent has this problem. To overcome this, we have to learn gradient descent with momentum. So that we will see later. If no, not today, later, but before finishing, one question that you have to think. So in logistic regression also, we have at first in logistic regression, what we have taken? Z equal to say maybe say W1x1 plus W2x2 plus B. So we have taken actually in terms of say theta 0 plus theta 1x1 plus theta 2x2. Same thing. And here also in logistic regression we did say then we fed it in terms of Z. We calculated, right? In neural network also what we have seen so far, here also we have done the same thing. Then also we calculated the sigmoid Z and do the same thing. Only some few changes were we took different loss function. Okay. Now the question is, are this logistic regression and the neural network we have seen so far are the same? So by obvious reason they are not. Okay, I am giving this question to you. So what should I comment? Those are same or no? So far we have seen in terms of different loss function. Apart from that, almost similar, right? Same thing. But neural network is giving us the freedom. Number one, use different kind of activation function that logistic regression will not give you. Logistic regression only one type of that sigmoid. Clear? So in some interview or anyone is asking you the same thing. So neural network you can use some different activation function that we will see later. Tan H activation function or ReLU, those leaky ReLU, those we may see different activation function. And in the optimization function, just we have seen gradient descent or gradient descent with momentum like other activation function we may also see, and different type of loss function. So again the concluding remark is So don't jumble up in between loss or cost function. These are your mean squared error, maybe mean absolute error, those things. Activation function, we have seen sigmoid, some other activation function may be tan H, ReLU in this way. And optimization function, okay, optimization function we have seen gradient descent with momentum, this way you will see. So there are different objectives. Activation function is achieving the non-linearity. Loss function, obviously the calculating the loss. And optimization function, what it is optimization? Optimize parameter. So okay, when someone is saying only parameter, by default please think of learning parameters, but for hyperparameters you have to explicitly mention the hyperparameters. Okay.